Greetings and welcome back to section 17. This is Picture This. And this is probably one of my favorite portions of this book here. Let's go into the slideshow. Okay, we're getting closer towards the end. Picture this. The name for a standardized representation of components in an electrical wiring diagram is called a schematic symbol. The symbols on an electrical circuit schematic diagram represent electrical components. It's kind of like the roadmap of what the circuit does. The way components are interconnected is accurately represented in the electrical circuits and schematic diagrams. So here's a bunch of schematic symbols. We got the resistors up here, fixed, variable, photoresistor, thermistor, which was temperature, tapped, adjustable. You have capacitors, electrolytic, variable, feed-through, split, non-polarized, fixed, inductors, air core. The iron core has the lines through it. Adjustable has the arrow through it. Anything pretty much adjustable has the arrows through it. See, you got your pots, which is adjustable, variable, variable cap that has the arrow through it. Here's a air core, iron core, and there's a little dot that indicates the phase relationship on your windings. So you'll see that on transformers. Here's some tubes, CRT, cathode ray tube, twin tubes. You have different buses, address buses, shielded coax wire, switches over here, lamps, the different symbols for ground, op amps, relays. This is thyristors, your SCRs, your triacs. Here's your bridge rectifier for diodes. The bridge rectifier converts your AC into DC. We covered that before in the previous slides. Diode rectifier, the LED, notice the arrows pointing out, indicating that it's emitting light. More adjustable, I'm sorry, these are transformers down here. So it has an air core transformer, iron core with the lines through it. Your transistors, FETs and MOSFETs, NPN, PNP, N channel, P channel. You have MOSFETs and Darlington transistors. This is MOSFET with a protection diode in it. Opto-isolators, batteries, logic, digital logic, and different types of jacks and connectors. So that's a whole bunch of different schematics, and there's more. This is just kind of general symbols that you might see. So in this chapter you have to identify some schematic symbols. And component 3. So if we look at component 3, that's a variable inductor. The inductor kind of is like a winding of wire, right? These are two variable caps. This is an antenna. By the way, this is a filter. The component in figure 4 is in T3 is an antenna. That's the upside down triangle. A capacitor is used together with an inductor to make the tuned circuit. Simple series resonant tuned circuit consists of an inductor and capacitor connected in series parallel. So this is series parallel, this is parallel resonance, or a tank circuit. So minimum resistance or impedance at resonance. This has a maximum impedance or resistance at parallel resonance. And in the general, radio license, it gets into more details on resonant circuits. So component 1 in figure T1 is a resistor. So in this schematic, this is a figure 1's a resistor. Figure 2 is a NPN, remember not pointing in, transistor. 3 is a light bulb. 4 is a battery. And these little pitchfork things, they're ground. So those are all connected together. The component number 2 in figure T1 is a transistor. The function of component 2 in the figure T1 is to control the flow of current. So we have a very little current coming into the transistor, a few microamps, and it's controlling a few amps. So we have something that's very, very tiny controlling something very, very big. Component 3 in figure T1 is a lamp. So that's a bulb or a lamp. Component 4 in figure T1 is a battery. It's a 2-cell battery. You see the positive, negative, so that's a 2-cell. Component 3 in figure T2 is a single-pole, single-throw switch. So this is a schematic of a power supply, a linear power supply. Here is your 120 volts AC in with a plug. Figure 2 is a fuse. Figure 3 is a switch. 4 is a transformer. 5 is a diode. 6 is a cap. 7 is a resistor. 8 is an LED. 9 is a pot. 10 is a Zener diode. So this is a half-wave rectifier right here. So we have one diode, and it's going to be positive pulses coming out of here, and this cap filters that out. 7 is a current limit resistor for the LED, because the LED is right around 2 to 3 volts, and if you're higher than that, you need a series limit resistor. 9 will adjust the voltage coming out of here. This guy is a Zener regulator, and that is a basic supply, basic linear power supply. Figure 2, component 4 in figure T2 is a transformer. So it's an iron core transformer. And again, the grounds, they're all connected together. Component 6 in T2 is a capacitor. And it's an electrolytic capacitor because it has the flat line and the curved line under it. Positives on the top, negatives on the bottom. Component 8 in figure T2 is a light emitting diode. Okay, so you got the diode symbol with the arrows coming out of it, emitting out of it. That means it's emitting light. Component 9 of figure 2.2 is a variable resistor or a potentiometer or a pot. A meter can be used to display signal strength on a numeric scale. So here is signal strength. A switch is controlled by electromagnet, describes a relay. A regulator is a type of circuit that controls the amount of voltage from a power supply. So instead of using a Zener diode, typically now you use a regulator. And for example, an LM7805 is a positive 5-volt regulator. And these are a lot more stable than your Zener regulators. You're a lot easier to work with as well. A component commonly used to change the 120 volts AC house current to a lower AC voltage for other uses is a transformer. So this is a step-down transformer. So it takes down 120 volts and steps it down to a lower voltage. It also provides isolation from your 120 volt main. The name of the device that combines several semiconductors and other components into one package is called an integrated circuit. 3 dB is the approximate amount of change measured in decibels of a power to increase 5 watts to 10 watts. So 3 decibels is either you cut it in half or you double it. Negative 3 dB, you cut it in half, plus 3 dB, you multiply it by 2. So here's your dB chart. So 3 dB, power ratio of 2. 6 dB, you multiply by 4. 10 dB, you multiply by 10. 20 dB, 100. 40 dB, 10,000. 60 dB, 1 million. And that's all plus. If you go to minus 3 dB, it's cut in half. Minus 6 dB, it's a quarter. Minus 10 dB, it's a tenth. Minus 20 dB, it's 1/100th. Minus 40 dB is 1/10,000th. Negative 60 dB, 1/1,000,000th. So there's your power ratio for the negative side. There's your power ratio for the positive side. You also have the voltage ratio in dB. So we're just going to concentrate on the power today because I think these slides only deal with power. The approximate amount of change measured in decibels of a power decreases from 12 watts to 3 watts is minus 6 dB. The approximate amount of change measured in decibels of a power increase from 20 to 200 watts is 10 dB. Okay, so here's our chart again. So negative 6 dB, so 12 divided by 4, right, gives us 3 watts. Let's see, 20 watts to 200 is 10 dB. So power increase, so that's plus 10 dB. You multiply it by 10. So 20 times 10, right, is 200. Okay, the abbreviation for LED stands for a light emitting diode. So inside there's a little LED chip, and it's encapsulated. This one happens to be a red. It's a gallium arsenide, and there's a heatsink inside. It's either aluminum or copper, and these are very, very, very efficient. A device commonly used for a visual indicator is a LED. So that's the most common use for indicators instead of bulbs, because one thing is they're very efficient. Two, they very rarely blow out, unlike a lamp, and they throw out a lot of light. Alright, so this is powers of 10. So we're going to get into a little bit of powers of 10. There's no calculations in powers of 10, but you still have to identify powers of 10. So in electronics we use engineering units. In this chart you're seeing scientific notation. So in engineering units we use 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12, 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, 10 to the minus 12. So you got 1,000, which is a kilo, which is K, a million, which is mega, with a big M, billion, which is giga, with a big G, and this is a relatively new term that has come about because of computer technology has gotten much larger in the hard drive space, is trillion, which is tera. So when I started electronics, we barely used tera at all. Now you hear it every day, terabyte. Let's see, the other direction, 10 to the minus 3, thousandths milli with a little m, 10 to the minus 6, which is a millionth, which is micro, the mu symbol, it's a little u, it's called a mu. 10 to the minus 9, which is a billionth, which is nano with a little n. 10 to the minus 12, which is a trillionth, which is pico with a little p. Another way to specify a radio signal is 1,500,000 hertz is 1,500 kilohertz. If the frequency shows a reading of 2425 megahertz, you can read it as 2.425 gigahertz. So we're just moving it over 3 decimal points over. So go from hertz to kilohertz, you move the decimal place over 3, and then it's 1,500 kilohertz. If we want to convert to megahertz, we move over another 3, that would be 1.5 megahertz. If there were 1,000 volts, it'd be 1 kilovolt. If an amp meter is calibrated in amps and it's used to measure 3,000 milliampere as a current, the reading would show 3 amps. So we want to go from milliamps to amps, go to the left 3 decimal places, 3 amps. Now if we're going the other direction, from kilohertz to hertz, we move to the right 3 places. So if you're going to go up in powers of 10, you go to the left. If you want to go down in powers of 10, you go right. So 28,400 kilohertz is equal to 28.4 megahertz. 28.4 megahertz. 500 milliwatts is equivalent to half a watt. 1.5 amperes is the same as 1,500 milliamperes. So again, move the decimal place over. We're going from amps to milliamps. We're going down in the powers of 10 scale. So 1, 2, 3 to the right. So that'd be 1,500 milliamperes. Okay, 1 million picofarads is the same as 1 microfarad. So we're going from 10 to the minus 12 to 10 to the minus 6. So 1, 2, 3, 4, 5, 6. So it'd be 1,000 nanofarads, or 1 microfarad. One millionth of a volt is equal to 1 microvolt. Rosin core solder is the best type of solder for radio and electronic use. You do not want to use the plumbing solder. Plumbing solder is a acid core solder, and it will eat away at the delicate copper that's in your traces and in your wire. I've done it in the past, and a few years down the line it's a big mess, and it literally eats away at the copper because it's so small. Grainy or dull surfaces is a characteristic of a cold solder joint. So that's a classic cold solder joint. It's dull in appearance, or grainy. It should be nice, bright, shiny, very smooth. Voltage and resistance measurements are commonly made using a multimeter. So a multimeter does a variety of things. It measures voltage. It's called a VOM, a volt-ohm meter, or a multimeter. So it measures volts, ohms, and current. This is an old analog one. With the old analog ones, you have to be careful with polarity because you can break the needle on the inside. If you have it hooked up backwards and the needle slams to the left, you can bend and break the needle. There's also a 0 ohms adjust, so when you go into resistance, you have to short your probes out, and 0, it'll go full, deflect full to the right, and you got to 0 it at 0 ohms. You can also measure, in this one, DC volts, AC volts, and DC current. So actually the analog ones are a lot more accurate. There's a mirror behind this that you line up the needle and the reflection, and that's how you get the accuracy out of this. The digital multimeter is less accurate. This guy might be 0.1% accurate. Your multimeter is probably about 0.5% accurate. For the hobbyist, doesn't matter. I would use the digital multimeter. It's a lot more forgiving. You can hook things up backwards, and it's only going to indicate a negative symbol for voltage. If you hook up the voltage backwards, it's not going to destroy anything. This guy is resistance right here. You don't have to zero anything out, or automatically zeros. You just switch to the range. And there's also auto ranging meters too. This is a manual range meter where you have to select the range that you want. There's auto ranging meters out there that you just put it in ohms and it automatically does the range for you. This one's one of the cheapo ones that you can probably get this meter for around $5–6. AC volts, you can measure AC volts, DC amps. This one you can measure current gain of transistors, you can measure frequency, and it has a continuity or a beep check for measuring low resistance. So and it runs off of 9 volts. This guy, the analog, usually have multiple batteries. They have a battery for the resistance, they have the battery for a couple other things in here. Usually it's a 9 volt and a D battery in this guy. This guy, I've seen meters use AA's, AAA's, 9 volts, and some standard batteries like that. So if you're starting out, go with the digital multimeter. So that's just my 2 cents. Take precautions when measuring circuit resistance to ensure that the circuit is not powered. So you don't want to measure circuit resistance when you have power on there. You're going to blow out your meter. Some of the new digital multimeters, if you use a name brand one like a Fluke, it does have protection circuitry in there. But some of the cheap ones, like the cheap Chinese ones, they don't have any. They have very little protection in there whatsoever. So let's see, that is a cat rating on here, and I don't see a cat rating on here on this one. Nope. There's category 1, 2, and 3 for meters, and that's a safety thing. So if you get the cheapo meters, that's okay if you're experimenting with low voltage, low power. But if you're doing anything with 120 volts or measuring anything like over an amp or so, get a good name brand like a Fluke, just for a safety. So anyways, measuring voltage when using resistance settings might damage the multimeter. When an ohmmeter is connected across an unpowered circuit, initially indicates a low resistance and shows increasing resistance with time that indicates the circuit contains a large capacitor. So when you have your resistance meter, your ohmmeter, in the ohmmeter setting, and you see very small resistance that starts increasing higher, 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 it's usually a cap that's in there that you're measuring. Alright, so we're going to go on to the Q&A section next. Picture this. See you then.